All right, here we got more of a consider this new situation that unfortunately will have ramifications later. The statement is, suppose that J of R, the current density, volume current density, is constant in time, but rho R of T is not. Conditions that might prevail, for instance, during the charging of a capacitor. Okay. A. Show that the charge density at any particular point is a linear function of rho R of T is equal to rho R of 0 plus the time derivative of the 0 point times T. Alright? Where rho dot R of 0 is the time derivative of rho at T equals 0. Alright? And then B, show that B of R is equal to, integral of JR prime cross R script R hat over script R squared d tau prime. Show that this obeys Ampere's law with Maxwell's displacement current term. Alright, so for part A, the continuity equation states that the change of rho with respect to T is equal to negative divergence of J. Here the right side is independent of T, so we can integrate. Alright, so set this up, separation of variables, then we get d rho on one side, dt on one side, and we're able to integrate this to get rho of T is equal to negative divergence of J, T plus C. This constant may be a function of R's. It's only a constant with respect to T, since that's what we integrated over. So putting in R dependency only, R dependency explicitly, and noting that the divergence of J is equal to negative rho dot R at T equals 0, we see that rho of T is equal to, we plug this in, negative rho dot T plus C, and the C is dependent on a position only, not time, and thus we see that we get this relationship. Which, after the fact kind of makes it look easy to understand, but not necessarily easy to show without this. But that continuity equation comes and saves our butts again. Alright, so B, suppose that E is equal to 1 over 4 pi epsilon naught, rho script R hat over script R squared d tau, and B is equal to mu naught 4 pi J cross R hat over R script R squared d tau. Alright, so what we want to show is that the divergence of E is equal to rho epsilon naught, and the curl of E is equal to the negative time derivative of B. Similarly, the divergence of B is equal to 0, and that the curl of B is equal to mu naught J plus mu naught epsilon dE dt, provided that J is independent of T. Alright, let's start working. We see that we have the divergence of E. Go ahead and plug that in. We see that rho is independent here of the coordinates d tau, so we were able to push that out. Now we're just left with the divergence of the script R, which we saw back in chapter 1 was equal to 4 pi the delta function cubed, so the three-dimensional Dirac delta. The 4 pi's cancel, and we see that the integral of the Dirac delta is 1, so we're left with rho over epsilon naught. That checks off. The curl here, same thing. Take the curl of the script R. We also showed here that that was equal to 0 back in chapter 1, so good thing we're equal to 0. What we need to do now is show that the time derivative of B is equal to 0, which is easy because B is constant in time. So the derivative of B with respect to time is 0, so that equation checks out. And we see that the divergence and curl of E equations are satisfied. From chapter 5, we know that the Biot-Savart law satisfies the divergence of B equals 0, using a similar method, but we got to be careful with the cross product and the J cross R hat terms. So now we need to check the curl of B. So similar arguments, what we say is that the curl of B cross curl of J cross R hat, we can split that up using I believe backcab or one of the vector identities. Again, those vector formula coming back with these triple products. And we see that we get J with the divergence of R hat over R squared, and then minus J dot nebula, the operator. I don't know why I'm saying nebula, the del operator in the r hat direction over r squared. We see that that's equal to the negative, or that's equal to the Dirac delta again. And then we're still trying to figure out what j dot del is. So with that, we see here that we can move that integral out only to the j dot del term with respect to the r hat, since we're already able to solve for the Dirac delta, shoving that j out, 4 pi times j. Now we're only left with the negatives here because what we're doing is putting in the prime coordinates, and with that we're able to see that we have mu naught j after the 4 pi's cancel plus mu naught over 4 pi integral j dot del prime r hat over r squared d tau. Integration by parts yields 2 terms, one of which becomes a surface integral and goes to 0. The other is r over r script r cubed del prime dot j, which we know is equal to negative rho dot. So, from the continuity equation, so what we're able to do is plug this in, and we see that we have mu naught j plus mu naught over 4 pi. Integration by parts yields the surface integral, which goes to 0, minus the integral here of r hat over r squared, negative rho dot d tau. Okay. So with that, we're able to kind of simplify even more. The negative signs cancel, and we can just go ahead and plug it away. We see that the rho dot is equal to d rho dt. Again, so we take that time derivative out. Pretty good there. And magically, maybe not magically, what we see here is that we have the time derivative of the field for E. That's awesome. Okay, we have to move the 4 pi epsilon naught over, but the integrals are the same. That's awesome. And so what we see here is that the 4 pi's cancel. We have a factor of epsilon, and well, the curl of B is equal to mu naught j plus mu naught epsilon naught dE dt, and the equations are satisfied. That's wonderful. A little messy with the integration by parts, but everything else is awesome.